Hi everyone, welcome back to Mind and Maths with Amna. In the previous lesson on differential equations, we covered first order differential equations and second order differential equations. And now we're moving on to coupled differential equations. And we're going to solve this using diagonalization. So suppose we have this question. First of all, we're going to convert it into matrix form, which is a fairly easy thing to do. We have the first derivative of y1 and the first derivative of y2 as a column vector, and then we have our 2 by 2 matrix with 7 minus 15 2 and minus 4, and we have a column vector with y1 and y2. So basically I have a system y dot is equals to ay, which is a homogeneous system. So we have a homogeneous system. Okay, the eigenvalues basically are satisfy this that AV is equals to lambda V, where V is known as an eigenvector that corresponds to the eigenvalue lambda. So basically we have A V minus lambda identity V is equals to 0, A minus lambda identity V is equals to a 0. To get the characteristic equation, I'm going to take the determinant of this and put it equals to 0. Oh, sorry, I spelled it wrong. Anyhow, so we need the determinant of a 7 minus lambda, 15 remains there, 2 minus 4 minus lambda, and we put the determinant equals to a 0. So what do we get? We get a 7 minus lambda into a minus 4 minus lambda plus a 15 into a 2 is equals to a 0. So we get a minus 28 minus 7 lambda plus 4 lambda plus lambda square plus 30 is equals to a 0, which amounts to lambda square minus 3 lambda plus 2 is equals to a 0. When we factorize it, we get a lambda minus 1, lambda minus 2 is equals to a 0. So therefore we have lambda 1 as 1 and lambda 2 as a 2. These are real and distinct roots. So moving on, our diagonal matrix basically has these entries on the diagonal. Therefore, our P matrix have to have the corresponding eigenvectors as its column. So I'll have V1 here as the first column and V2 there as the second column. Traditionally we put dotted line here to denote that there's a vector here. Okay, solving for the first one, we'll get a minus lambda 1 into v1 is equals to a 0, and this was the matrix that we're going to solve. So let's start doing it. The value of lambda in this scenario is a 1, and I want to solve this equation. I'll just write v1 as xy, and I'll write a 0 0 here. When I substitute in the value of lambda 1, I'm going to get a 6 over here, a 6 over here and minus 5 over here. So we can solve this system by any method that we like. I'm just going to do row operations. So I'm going to first basically just multiply row 2 with 3, and then I'm just going to subtract it. Okay, so I'm just going to do this first, so that I'm left with a 16 minus 5, 0, 6 minus 15, 5, and therefore we get a situation where we have infinite many solutions. Let me write it down. We have a row 2 minus a row 1. If I run this operation, then I'll be left with a all 0 row. This basically means that we have two unknowns but only one equation. We needed two equations, so therefore there are going to be infinitely many solutions. Infinitely many solutions. So therefore what I can do is I can express this as I can take y as any variable t. Okay, I have a 6x minus 15y is equals to a 0. 6x is equals to a 15y. So x is equals to a 5 by 2. Y. If I take y as a 2, then I'm going to end up with the x value of 5. I want to avoid a fraction. So v1 is equals to a 2 and a 5. So this is our first eigen vector. Now let's find the second eigen vector. It's going to be the solution to this. However, for the value lambda 2 is equals to a 2. So let's do that. So now I want to find the same thing but for lambda 2. So we have a lambda 2 identity v2 where lambda 2 is equals to a 2. Therefore what we get here, we'll get a what was that? We had a 7 minus a 2, right? So we're going to end up with a 5 and we'll have a 15 there, 2 and minus 6 here. Okay, again let's just do row operations. I'm going to put in the augmented form, and this is the augmented form, and I'm going to actually we can multiply the first row by 1 by 5, and I can multiply the second row by half, and I can run both of these to get 1 minus 3, 1 minus 3, 0, 0. And now when I do a row 2 minus a row 1, I'll be left with again all 0 row. All 0 row, which indicates infinitely many solutions. So we have x minus 3y is equals to a 0, x is equals to 3y. If I take y is equals to a 1, I'll get a x is equals to a 3. So therefore v2 ends up being 1 and 3. So in conclusion, when we have a matrix A which is 7 minus 15, 2 minus 4, D is equals to 1 0 0 2, and P will end up being 5 3 2 1. There's also an interesting case when A transpose is equals to an A, so we have like a symmetric matrix. This is an interesting case where we say the matrix is orthogonally diagonalizable. We'll study this in lectures on linear algebra. So we end up with linearly independent vectors in the P matrix. But for now, I don't think we need to know that. Okay, anyhow, now that we have this information, we can solve our original question, which was this, using all of this information. So this was our main concern. And now we have all the data that we need in order to solve this. So let's do it step by step. This was the system that I needed to solve. I'm going to do a change of variable. I'm going to say, suppose that y is equals to pz, so that the first derivative will be p into first derivative of z. Hence, when we have a y dot is equals to a y, I'm going to substitute this here, and I'm going to substitute this over here, and then I'll be left with p z dot a p z. Z dot will be p inverse a p z, and since we just said that it's A is a diagonalizable matrix, therefore P inverse A P is equals to the diagonal matrix T, because A is diagonalizable. So therefore we have a Z dot is equals to dz. This gives us a very simple first order differential equation, which is extremely easy to solve. So let's begin. Suppose I have z1 dot, z2 dot. The dot basically here represents the first differential, and the D matrix is a 1 0 0 2, and then I have a z1 z2. When I do matrix multiplication, I have a z1 here and a 2z2 here. Therefore, we have a simple system, and the solution to this is, we know z1 dependent on time is the value of z1 at time t, e power t, and z2 is equals to 2z2. We know this is a simple system, and we know the solution for this is going to be the initial value of z2 e to t. So therefore now we are in a place where we can write out our final solution. So we know that we had taken y is equals to pz, and we figured out what z is, right? So we'll through this we'll know what the answer is. So y1 y2 is what we needed to find out. P matrix was the matrix consisting as eigenvectors as its column, and z, we just found out what z is. Okay, so once I open this row into column, z1t is basically 5. Y1t is equals to 5 into z1 at 0 e power t plus 3 z2 at 0 e power 2t. Then y2t is a 2z10 et plus a z20 e2t. As you can see, we have unknowns over here, right? So we have z10 and z20, which are unknowns. You cannot find these unknowns unless the unknown initial conditions for y1 and y2 is given. So you can find these by using the same equation here, but saying that you're analyzing this at time t0. So basically you have a y1 at time 0 and e power 0 is equals to 1. So basically we're left with this. So you can, if you know this, if the question has given you this, if this is given, then you can easily find these unknowns. You can use the you can make the augmented matrix, or you can use the Kramer's rule, or you can just find the inverse and multiply it through. So for instance, I've already done the Kramer's rule and also augmented matrix. So let's just this time multiply it by the inverse. The inverse is going to be a 5 minus a 6, 1, 5 minus 2, 3, and I have to multiply it by the initial conditions which could be given in the question. So therefore the answer would be a 1, minus 1, minus 3, 2, minus 5 multiplied by these initial conditions, and therefore you'll find your unknowns. So this was a question in which the functional form of was given. So you had like these constants were actually not unknown. But what if you get a question in which these are actually unknown? So you have like a generic equation which is given to you for you to solve. So suppose you get a question along this format. It says that the coefficient is a11 x1, a12 x2 plus some constant g1. Then the next is x2 dot a21 x1 plus a22 x2 plus g2. Again, you convert it into matrix form. You say this is x1 dot x2 dot, then you have a 2 by 2 system with a11, a12, a21, a22, and you have a x1 here, x2 there, and then you have a g1 here, a g2 there. So you have a system like this. X dot is equals to a x plus some constant g. Okay, so since g consists of simply constants, therefore for the particular solution we can assume that we have a constant solution. Therefore the derivative is going to be a 0. So we have a 0 here, you have an ax bar here plus a g there. Therefore you have a ax bar is equals to minus g. So you get an AX is equals to A inverse of G. Sorry, G. So what is this going to look like? For instance, I have the matrix A. I'll first need the determinant A11, A22 minus A21, A12, and then I switch these and I change the sign here. And what was G? It was this column vector. Since this is a 2 into 2 matrix and this is a 2 into 1 column vector, therefore when we multiply it, you're going to get what? You're going to get a 2 into 1 column vector. So I'm saying when you do when you multiply this, when you do matrix multiplication, you're going to end up with a column vector. We can call this x1 bar, whatever the answer comes, x2 bar. These are constant solutions. Therefore, we say that the particular solution is the constant solution x1 bar, x2 bar. So we're done now with the first part. Second, moving on to the homogeneous solution. Remember, for the homogeneous solution, we solve the solution for the column vector G is equals to 0. So we have x dot is equals to AX left. So we are solving this and we put in the trial solution. We say we have a trial solution. We can say it is x is equal to some constant matrix of constants, this, and E lambda t. Therefore the derivative would be lambda b E lambda t. Putting it into the main equation, x dot is equals to AX, we get lambda b E lambda t. And basically, just so there's no confusion, and I'm putting this here and I'm putting this here. Okay. I have a b E lambda t. Okay, then I have a b E lambda t minus a b E lambda t is equals to a 0. So a minus lambda identity into b E lambda t is equals to 0. This is a non-zero matrix. We know that this is always greater than 0. So basically we're going to take the determinant of this matrix and put it equals to 0. And this is going to give us lambda 1 and lambda 2, which are basically two eigen values. And we're just going to say that the eigen vector corresponding to lambda 1 is v1, and where we can say v1 is equals to 1v, and then we can say the eigen value eigenvector corresponding to the eigenvalue lambda 2 is, you can say, a 1 and a u. So therefore we had a matrix A which was A11, A12, A21, A22. We ended up with a diagonal matrix with lambda 1 0, 0 lambda 2, and we had a P matrix, the first column V1, second column U1. So the same logic carries forward to this. We're going to do a change of variable. I'm going to assume that x is equals to pz. Therefore x dot will be equals to p z dot. Our main equation was this, x dot is equals to ax. I'm going to put these here, substitute both of them down, and I'm going to be left with a p inverse a p z. So we have the diagonal matrix here. We're almost done. Hopefully this wasn't difficult. So this was the first, second, and we have the diagonal matrix, which was lambda 1 0 0 lambda 2, and then we have z1 z2. I'm trying to like hurry because I don't want the video to be too long, because lengthy videos can be very tiring to watch. Anyhow, we get a simple first order differential equation, and the solution to which we know is like this: first and e lambda 1 t. And let's do it again for z2. Looks like a 2. Z2 t will be the initial condition of z2 e lambda 2 t. Yay, the final step. We have our final answer. X is equals to p z, and therefore this was the homogeneous solution. Okay, so x1 homogeneous t, x2 homogeneous t is equals to the matrix P, which was 1 v 1 u, and we just said, let's just write this as c1. There's just a constant here and there's just a constant there, just for simplicity. So we have the homogeneous solution here. So what is the particular then? We had the, let's write it down. We found out the particular solution for the first was a x1 bar, and now we found out the homogeneous solution, which is a v c1 e lambda 1 t plus u c2 lambda 2 t. And for the second x2, the particular solution was an x2 bar, and now we can see the homogeneous solution is a c1e lambda 1 t plus c2e lambda 2t. The general solution is always the homogeneous plus the particular. So the general solution is always the homogeneous solution plus the particular solution. So we have our answer. We have a x1t is equals to v c1 e lambda 1 t plus u c2 e lambda 2 t plus x1 bar, and then an x2 t, and we have a c1. Just going to be lazy and I'm going to just copy paste so I don't have to write it all over again. We're going to get this, and this is our final solution. Remember, for stability, the limit of e lambda t as t approaches infinity will be equals to 0 if and only if the lambda value of lambda is negative. Therefore, in this model, stability condition is that lambda 1 and lambda 2 both are equals to a 0. So this is the stability requirement. I'll make another lecture for when one root is unstable and the other is stable. Then we end up with a saddle solution I'll make another video on this. For now, this covers everything that I wanted to cover in today's class. And I've also, as an added resource, solved an example which is basically a 3 by 3 system to show how the method scales. But instead of like making this video longer, I've just placed a full word solution in the notes. You can find the downloaded and download the link in the that I'm going to place in the comments. So I hope this topic wasn't difficult, and see you next time. Take care.